Okay, good afternoon, students. So we'll be here today to resume the Chemistry Olympiad training from where we left off. So we had left off with reactions of acids, the three reactions of acids, namely acid plus metal, acid plus base, and acid plus carbonate. At this juncture, you should be familiar with how to balance chemical equations. Okay, so you have learned how to balance chemical equations in your lessons itself, as well as during Chemistry Olympiad training. So we shall continue this skill of balancing equations in the reactions of bases. So now we will start by talking about bases, which is on page 13 of the set 5 notes. So what are bases? Now a base you recognize from its name because a base is any metal oxide or hydroxide. So the keyword here is oxide or hydroxide. Okay, oxides of hydroxides of metals. So take, for example, magnesium oxide. Magnesium is a metal, so magnesium oxide is a base. Copper 2 oxide, copper is a metal, so copper 2 oxide is a base. Not just oxides, but also hydroxides. So take, for example, magnesium hydroxide is also a base. Sodium hydroxide is also a base because magnesium and sodium are both metals. So what are some common bases we have in the lab? We have sodium hydroxide. This is a common base we have in the lab. Formula NaOH. All right, so Na plus OH minus. Another common base, potassium hydroxide, KOH. All right. Next, we have calcium hydroxide. Now, calcium is not Ca plus, calcium is Ca2 plus because calcium is from group 2. So the formula for calcium hydroxide is Ca bracket OH2. Okay, so these are the three common hydroxides that we have in the lab, which are bases. You know they are bases because they are hydroxides of metals. Okay, now calcium hydroxide is another name. Calcium hydroxide's name is lime water. Okay, lime water is aqueous calcium hydroxide. And lime water is what we use to test for the presence of carbon dioxide gas. We bubble the gas into lime water. If a white precipitate is formed in lime water, then it's carbon dioxide gas. So lime water is used to test for carbon dioxide gas. Okay. Now, as mentioned, bases is not just hydroxides. Bases also include oxides of metals. So calcium oxide, CaO, is also a base. Copper 2 oxide, CuO, is another base. Okay, so bases are basically metal oxides or metal hydroxides. Now, so why do we give this word base? Because bases, they react with acids to produce only salt and water. So if I were to react sodium hydroxide with an acid, it will produce only a salt and water. So we can come to the conclusion that acid plus base gives you salt and water. And this reaction's name is called neutralization. Okay, so this we actually covered last session, acid plus base. This reaction is called neutralization because only salt and water are formed, both of which are neutral products. Now, we have also learned this word alkalis in secondary 2 when you learned chemical reactions for the first time. So what is an alkali? How is it different from a base? Well, alkalis are soluble bases. This means that alkalis must dissolve in water. Okay, so alkalis are soluble bases that dissolve in water. Okay, meaning the state symbol must be aqueous. Alkalis must be aqueous because they are dissolved in water. But it doesn't just dissolve in water. It needs to dissociate and ionize in water to give hydroxide ions. So you realize that alkalis, not only are they bases, there's one additional condition, which means they must be dissolved in water. Okay, so it's not just a base. It's a base that dissolves in water and dissociates and ionizes to give OH minus ions, which you can see in the equations below. NaOH forms Na plus OH minus. Now, the interesting one, of course, is the last one, NH3. Now, NH3 is also known as, the name of NH3 is ammonia. So aqueous ammonia is an alkali because aqueous ammonia is able to dissociate and ionize to give OH minus in water. We say that aqueous ammonia is an alkali. However, you realize that it has a reversible arrow sign. So if you recall from the previous lesson on acids, acids that dissociate partially and reversibly, we say that they are weak acids. So in this case, aqueous ammonia dissociates partially and reversibly. So aqueous ammonia is a weak alkali. Okay, because it dissociates partially and reversibly in water to give a low concentration of OH minus ions. Okay. Now, we already know that alkalis, they taste bitter, they will turn red litmus paper blue, okay, and we have gone through some of these common alkalis, okay? Now, let's go straight to the reactions of alkalis. Well, the first reaction really is the reaction of alkali with ammonium salts. So you recall what is ammonium? Ammonium ion has the formula NH4 with a +1 charge. Okay, so ammonium is NH4 plus. So, for example, sodium hydroxide is an alkali. So sodium hydroxide reacts with ammonium chloride. So what is formed is salt, water, and ammonia gas. So in this case, sodium hydroxide plus ammonium chloride. Sodium hydroxide plus ammonium chloride will form sodium chloride. That's a salt that you form, plus water plus ammonia. All right. How do I work out that the salt is sodium chloride? Well, the salt's name always begins with the metal. So you always have to ask yourself, when naming a salt, what is the metal? The metal in this case is sodium because you had used sodium hydroxide. So the salt's name must begin with sodium. Sodium hydroxide, so the salt's name begins with sodium. Next, what's the second part of the salt's name? The second part of the salt's name comes from the ammonium salt that you used. So ammonium chloride will give sodium chloride. If you had used ammonium nitrate, you will get sodium nitrate, and so on and so forth. All right, so it produces sodium chloride, water, and ammonia gas. You need to know how to test for ammonia. Now, ammonia is alkaline. So we can place a piece of moist red litmus paper at the mouth of the test tube. Okay, so it's important that we place it at the mouth. We don't insert the litmus paper the whole way into the test tube. You only place it at the mouth, at the top of the test tube. Okay, the moist red litmus paper turns blue. Ammonia is alkali, so the moist red litmus paper should turn blue. Okay, so hopefully for my Sec 4s, this is a revision for you. We learned this once last year under acids and bases, how to test for the different gases. We also learned it in the second chapter called qualitative analysis, where we learn how to test for gases and ions. Okay, so please don't forget these chemistry that you have learned. Okay, so now let's try the quick check, where you have to write the chemical equations to represent the following reactions. Okay, so this is a demanding exercise because now you need to apply the knowledge. So now you realize that you have used potassium hydroxide, right? So if you use potassium hydroxide, the salt form is potassium something, right? Potassium what? The second part of the salt's name comes from the ammonium salt. You had used ammonium chloride, so the salt is potassium chloride. Okay, The other products are water and ammonia. So this is the word equation. Potassium hydroxide plus ammonium chloride forms potassium chloride, water, and ammonia gas. The chemical equation, KOH is potassium hydroxide, ammonium, NH4 plus 1 charge, chloride, Cl minus. So the formula is just NH4 plus, Cl minus, NH4Cl. Okay, potassium chloride, potassium group 1, so it's K plus, chloride Cl minus, so it's KCl. Plus water, H2O, ammonia. Ammonia don't have charge, it's just NH3. So ammonia is NH3, ammonium is NH4 with a plus charge. Okay? So this is the first equation. Now the second equation, sodium hydroxide plus ammonium nitrate. So again, metal is sodium, so your salt begins with sodium. But this time round, is sodium what? What is the second part of the salt's name? The second part of the salt's name comes from what ammonium salt you had begun with. You had begun with ammonium nitrate, so it's sodium nitrate. Okay, so the salt form is sodium nitrate. Sodium, because you have used sodium hydroxide. Nitrate, because you had used ammonium nitrate. Okay, so you must learn to link, make these links. All right. And always remember the salt's name begins usually with the metal. So in this case, sodium is the metal. So sodium, then nitrate. Okay, plus water plus ammonia. So plus water plus ammonia doesn't change because it's fixed. Okay, alkali plus ammonium salt forms salt, water, and ammonia gas. So now if you translate into chemical formula, sodium hydroxide is NaOH. Ammonium, NH4 plus. Nitrate is NO3 minus. So remember, nitrate is NO3 minus. So NH4 plus 1, NO3 minus 1. So NH4, NO3. Okay, so this is the chemical formula. Then sodium nitrate, Na plus, NO3 minus, plus water, plus ammonia. Okay, so far you realize the equations are balanced as they are. Okay, the equations are already balanced if you count properly. But let's look at the last one. Okay, reaction between potassium hydroxide and ammonium sulfate. All right, the reaction between potassium hydroxide and ammonium sulfate. So now the metal is potassium, so you will need to begin your salt's name with potassium. But potassium what? The second part of the salt's name comes from the ammonium compound, ammonium sulfate, so it's potassium sulfate. Plus water, plus ammonia. And this is where you really need to use all the skills you have in balancing equations, because you immediately realize, okay, the formula is actually not so straightforward. It's ammonium, NH4 plus. Sulfate though is SO4 2 minus. So immediately you realize the formula is not so simple. It's not NH4SO4. Because the positive and negative charges are not the same, right? NH4 only has a plus 1 charge. Sulfate has a 2 minus charge. Charges are not balanced, so I must have 2 ammoniums, 2 NH4. So NH4 bracket 2. 2 ammoniums for each sulfate. Because ammonium is only plus 1. Sulfate is already minus 2. Okay. Next, we got to do the same thing. Potassium, K. Potassium is group 1, so it's K plus. Because group 1, they lose 1 valence electron. When you lose 1 valence electron, you become positive 1. But sulfate is 2 minus. So again, formula is K2SO4. There's no bracket here because K is not polyatomic. Ammonium, NH4, is polyatomic, so you need a bracket around it. Plus H2O plus ammonia. This is not balanced. How do you know it's not balanced? Because you look at the atoms. I got 2 ammonium. If I got 2 ammonium to balance it, I need 2 NH3 on the right. Okay, 2 NH3 on the right. 2 ammonium, 2 ammonia. Next, it's quite obvious I will need 2 KOH to balance out the potassiums, right? 2 KOH on the left, then you can have K2SO4 on the right. Now, I hope my SJChO remember this. When I taught you this last year, I've taught you a shortcut as well, or a pattern to note. If you got 2 hydroxides, you must have 2 H2O. If you start with 2 OH, you must have 2 H2O on the right. Okay? And so with that, we have learned how to balance the chemical equations for alkali plus ammonium compound. At this juncture, I hope you are doing fine. If I'm doing fine, can you please give me a thumbs up so that I know that you are following? Okay. Great. So let's move on. And the next part is on ionic equations. I will actually skip this because actually the ionic equation for acid alkali neutralization is just H plus OH minus forms H2O. The 2 is a subscript at the bottom. Okay. Now, regardless of the acid or alkali used, the ionic equation for acid alkali neutralization in the aqueous state is just H plus OH minus forms H2O. Okay. Now, the SJC3s, you have just learned ionic equations with Miss Ng and Miss Shahida in class. So I would advise you to practice page 15, page 16 on your own. My SJC4s, we should also practice page 15 and page 16. If you turn to page 16, not everything is acid plus alkali. Some are acid plus metal, some are acid plus carbonate. So I would strongly advise you to practice this on your own, okay, for my SJC4s. Okay, later on, I'll also put the answers in and I'll alert once the answers are in. Okay, but let's quickly power on past ionic equations. Let's go to page 17 and talk about pH. Now, the pH scale is a scale of numbers. It ranges from 0 to 14. Actually, this is not exactly true as well. The pH scale is actually a scale of numbers. It need not start at 0. It need not end at 14 because pH has a formula. pH is a negative logarithm. Whenever you see P in a chemistry mathematics formula, P actually means negative log base 10. Okay, so pH is negative log base 10 concentration of H plus. When we use square brackets in chemistry, we actually mean concentration of something. So in this case, concentration of H plus. All right. So for the SJC3s, I think you have not started logarithms. For the SJC4s, hopefully you realize again, this is where AMATS and chemistry are linked. pH is a negative logarithm. Okay. So what does this mean? Because it's negative log, it means that the higher the concentration of H plus, the lower the pH. Because there's a negative sign, the more H plus, the more concentrated the H plus, the lower the pH. Then now it makes sense. Oh, that's why acids have lower pH. Because acids dissociate and ionize to produce H plus. So more acidic, higher H plus concentration, hence lower pH. Okay? So finally, it makes sense. That's why your teachers taught you acids have lower pH. Acids have pH lower than 7. Why lower means acidic? Because more acidic, higher H plus concentration. Higher H plus concentration, lower pH. Okay? And so we come to the conclusion. Acids have higher H plus, lower pH. Higher H plus, lower pH. But then importantly, you see something else that's peculiar here. Under acids, we say acids higher H plus. This makes full sense. We know this. Acids dissociate to form H plus. How come suddenly Mr. So also included OH minus? This is because acids actually still contain a little bit of OH minus. But why? Why is there OH minus? There is OH minus because the acids are dissolved in water. You have to remember that these are all aqueous solutions. Aqueous means there is water. Water itself can ionize reversibly. So the OH minus actually came as a result of water, the solvent, ionizing on its own to form a little bit of H plus, a little bit of OH minus. So acids still contain a little bit of OH minus, just that the OH minus is lower concentration than the H plus. So it's not correct to say acids have no OH minus. It has a little bit of OH minus. The little bit of OH minus comes from water. Then you must be thinking, oh, so is water acidic or is water alkaline? Water produces H plus. Is it acidic? The answer is no. Do you realize water produces equal concentrations of H plus and OH minus? When water dissociates, it produces one H plus, one OH minus. It's equal concentrations of both H plus and OH minus. When it's equal concentrations, we say that it is neutral. And that's why since Sec 2, your teachers would have taught you water is neutral. The reason why water is neutral is because it produces equal concentrations of H plus and OH minus. Okay? Now, I spent some time on this because for pure chemistry, generally we like to test this. We like to test to see whether you know acids have higher H plus, lower OH minus. It is not correct to say acids have no OH minus. It has some, just that the OH minus is less. Okay? The next thing we like to test is, do you know why water is neutral? Water is neutral because it produces equal concentrations of H plus and OH minus. Okay? So at this juncture, have I made myself clear? Are we doing okay? We are doing okay. Can you please give me a thumbs up? Okay, thank you. So for my Sec 4s, I hope you realize this was exactly your end of year exam question last year. Okay, actually I asked you all right, explain why water is neutral. Just 1 mark. And that 1 mark you had to write, water produces an equal concentration of H plus and OH minus ions. Okay, that's why it's neutral. Okay, for the next page, I'm sure you'll recognize it. It's the common pH values of different common substances like gastric juices, fizzy drinks, and so on. Okay, now how do we measure pH in the lab? We can use a pH meter, otherwise we can use indicators. There are many indicators we can use. Litmus, your litmus paper is an indicator. Methyl orange is an indicator, and so on. So some of these indicators, we will use them in experiments like titrations later on. Okay, now let's move on to page 19. We also have universal indicator whose colors you should be familiar. Now your notes are obviously not colored. If you want the colored set of notes, please go to your Chemistry Olympiad 2023 notebook in OneNote. You will be able to see the notes in full color. Okay, to note, acidic. In acidic solutions, universal indicator turns red, orange, or yellow. In alkaline solutions, the universal indicator turns blue or purple. All right. Next, why is pH so important to know? Because the pH of soil is important. The pH of soil has to be controlled within a certain narrow range of values. It cannot be too low, it cannot be too high. All right. If it's too low or too high, you need to add calcium hydroxide. Let's cancel away calcium oxide. Let's add only calcium hydroxide to increase the pH value. All right. How does this work? It works because calcium hydroxide is a base. Right? We just said that metal oxides, metal hydroxides are bases. So calcium hydroxide is a base which will neutralize excess acids in the soil. And when you neutralize the acids, low pH. After neutralizing it, you will help to increase the pH. Okay, so at first the pH is too acidic, too low, like pH 3, pH 4, too low for plants to grow. By adding calcium hydroxide, which is a base, you neutralize the acids and hence you increase the pH. Okay. Now, please cross out calcium oxide. For the O levels, we would like you to know that calcium hydroxide is what is commonly added. Okay, we commonly add the hydroxide, not the oxide. Now, we move on to the very last section of acids and bases, which is on types of oxides. Now, we have zoned in on oxides. Reasons being, oxygen is all around us. You have oxygen in the air. The oxygen in the air can react with different elements to form compounds of oxygen. The compounds are obviously called oxides. So you think about it. For example, sodium plus oxygen forms sodium oxide. Carbon plus oxygen forms carbon dioxide, still oxide. Okay, so oxides can be divided into two broad categories, metallic, non-metallic. But when we ask you for a type or nature of oxide, what we are referring to is their acidic and basic properties. So important to know, many students get confused. They thought type of oxide means metallic, non-metallic. No, we are asking you for the nature or the type of oxide in terms of acidic basic properties. Okay, so let's now start. Basic oxides. Basic oxides are metal oxides. So if you know it's a metal, calcium oxide, basic. Sodium oxide, sodium is a metal, so basic. Okay, so metallic oxides are basic. Metallic, basic. Now, because it's basic, what it means is that it's a base. It will react with acids. Base can react with acids to form salt and water. Okay. Next, we move on to the other extreme, acidic. So we are on page 21. That's the last page already. Acidic is the opposite of base. Acidic is formed by non-metals. Non-metal oxides are acidic. non-metal, acidic. Okay, so obviously, non-metal oxides are acidic. Acids react with base. So like carbon dioxide, carbon is a non-metal, so carbon dioxide is acidic. So carbon dioxide reacts with bases like sodium hydroxide. Okay, next, amphoteric. Now we go to amphoteric. Amphoteric is interesting. It's just 3 specific metallic oxides. What are the 3? Zinc, aluminium, lead. These 3 oxides are amphoteric. Z-A-L, ZAL. Zinc oxide, aluminium oxide, lead-2 oxide, they are amphoteric. What it means is they can react with both acids and alkalis. Zinc oxide can dissolve in hydrochloric acid. Zinc oxide can also dissolve in excess sodium hydroxide, meaning it reacts with both acids and alkalis. Now, this one is what my Sec 4s also learned last year. But can we now add a few more to this list? So as chemistry Olympiad students, you should be prepared to do a little bit more. Now, are these the only metals, zinc, aluminium, lead? Are these the only metals that form amphoteric oxides? The answer is no. There are other oxides that are amphoteric. Another one is chromium. But chromium 3 oxide. Now, chromium 3 oxide is Cr2O3. Cr2O3 is also amphoteric. Okay, so let's take this down. Chromium 3 oxide is also amphoteric. Okay, now over here, Mr. So is talking about oxides. So zinc oxide, lead-2 oxide, aluminium oxide, chromium 3 oxide. But this amphoteric behavior also extends to their hydroxides. So they are also amphoteric hydroxides. Okay, so it also applies. So zinc hydroxide is also amphoteric. Aluminium hydroxide, AlOH3, is also amphoteric. Okay, it's AlOH3 because Al3 plus OH minus. Lead-2 hydroxide, also amphoteric. So similarly, you can easily predict chromium 3 hydroxide, Cr3 plus. Remember the 3 means 3 plus. So CrOH3, these are all amphoteric, meaning they react with both acid and alkali. Okay. And so for my Sec 4s, remember under QA we learned how do you test for zinc ions, aluminium ions, lead-2 ions? The way to test for zinc, aluminium, lead-2 ions is to add sodium hydroxide. When you add a few drops of sodium hydroxide, you will first form the white precipitate. The white precipitate is zinc hydroxide, aluminium hydroxide, lead-2 hydroxide. Right? The precipitate is always the hydroxide. But because these hydroxides are amphoteric, if you add excess sodium hydroxide, they will dissolve in excess sodium hydroxide to form a colorless solution. Okay? So for my Sec 4s, you last learned this under QA. So please revise. Okay? So we have finished amphoteric. The last one is neutral. So as the name suggests, neutral means they don't react with acids or bases. So what is neutral? Water is a good example. Water is neutral, pH 7. Other than that, carbon monoxide, also neutral. Nitrogen monoxide, also neutral. Another one, N2O. N2O is dinitrogen monoxide, is neutral. Now, this is also known as laughing gas. So later on, you can Google, how come this gas laughs? Okay, go and Google what laughing gas is. N2O is laughing gas, it's also neutral. Okay, so we are doing good on time. It's 5:45. Okay, so let's summarize. There are 4 types of oxides, namely basic. Sorry, let's write below. The first type of oxide is basic. Then you have acidic. Okay, then amphoteric. And finally, neutral, right? So do they react with acid? Do they react with base? Let's take a while to copy down this table and summarize it together, okay? Whether each type of oxide will react with acid, or will it react with base, or will it react with both? Okay, so let's summarize together by drawing this table out. For my Sec 4s, this is a really good revision for you now, okay? Hopefully, we are still familiar with types of oxides as Sec 4 students. Okay, so let's start with basic. Basic oxides. Basic oxides are metal oxides. Basic is a base. Base plus acid can. Base plus acid got reaction. So basic oxides can react and dissolve in acids. Because base plus acid, okay, can react. However, basic oxide plus base plus base, no reaction. You have not learned a reaction that is base plus base. You have only learned acid plus base. Remember, must be opposites of each other, then can react together. Acid react with base. Acid cannot react with acid. Similarly, base cannot react with base. So that's the first row. Basic oxides only react with acids. The next row, acidic oxides are non-metal oxides, like carbon dioxide, sulfur dioxide, nitrogen dioxide. These are all non-metal oxides. They are acidic. Acid cannot react with acid. How can acid plus acid react? There's no reaction. So CO2 doesn't react with acids. But acidic oxides, do they react with base? Acid, does it react with base? Yes, acid plus base. From salt and water. So the first 2 rows are settled. Basic oxides only react with acids. Acidic oxides only react with bases. Next, amphoteric. Amphoteric reacts with both. That's the one that can go with both acids and bases. So our amphoteric is the zinc, aluminium, lead. And today you learn one more, chromium 3. Chromium 3 oxide is amphoteric. Finally, neutral, as we just mentioned, water, carbon monoxide. They do not react with acids or bases. Neither acid nor bases. Okay? So this summary table hopefully will be useful in consolidating your understanding of the types of oxides. Remember, when we ask you for type of oxide, 4 types: basic, acidic, amphoteric, neutral. Okay? That's what we mean by type of oxides. Okay, and with that, we have finished the entire chapter on acids and bases. Okay, at this juncture, can I just check that everyone in the Zoom meeting, we are doing fine? If it's fine, can you please give me a signal that it's fine? Okay, good. So for my Sec 4s, I'm sincerely hoping this is a good revision for you. All right. Okay, so we have finished acids and bases. Now let's go on to set number 6. which is on the periodic table. Now, many of the things that I'll be teaching in set number 6 is also, again, a repeat for many of you here. However, a lot of it we will delve a little bit deeper today. So if I may move on to set number 6, let's have it in front of us. I will take the next 40 minutes to go through periodic table together. Now, the periodic table, all of us have encountered it since Sec 1. When you were first introduced to elements, you have been told that elements are arranged in the periodic table. We are able to find elements in the periodic table. What this means is, if you turn to page 2, the periodic table contains elements, not compounds, not mixtures. If you can see it in the periodic table, it means it's an element. So sodium is an element, scandium element, chromium element, right? So these are all elements. However, you don't see things like sodium chloride. Sodium chloride is not in the periodic table because sodium chloride is a compound made up of sodium and chlorine. Next, you don't see things like steel, S-T-E-E-L. Steel is not in the periodic table because steel is a mixture of iron and carbon. All right, so the periodic table only contains elements. Now, there are supposed to be 118 elements, all right, but of course, more elements are being discovered day to day. All right, more elements are being discovered. Now, this is the old syllabus periodic table, which the Sec 4s are doing. You're the last batch doing this syllabus. This is the old periodic table where group numbers are written in Roman numerals. So group 1 is written as group I, then group 2 is written as II. Okay? For the Sec 3s, you are using the new periodic table. The new periodic table orders the groups from group 1, group 2, all the way to group 18. All right, so you can see in the notes here, I'll be referring to group 1. Then after that, I'll say group 7 or group 17. So please understand the all here is because the periodic tables used by the Sec 4s and the Sec 3s are different. Okay, now I will leave you to read the periodic table on page 2 yourself. Much of it is already summarized for you. Now let's go to page 3. I think it's quite obvious. Let's do a quick revision on page 3. State the order in which elements in the periodic table are arranged. They are arranged. The elements are arranged in order of increasing proton or atomic number. Okay, so it's important to know the elements are all arranged in consecutive increasing proton or atomic numbers. So proton and atomic number is the same. Okay, next, question 2. Describe how the electronic structure of an element is related to the group and period in which the element is found. So let's tackle it one by one. First, the number of valence electrons determines which group the element is found. Okay, so hopefully we remember this. Number of valence electrons is group. Okay. Then what is period? Period is the number of filled or occupied electron shells. Determines the period. Of the element. Okay, so these are the 2 points. Valence electrons, group. Number of filled electron shells, period. Okay, next, we often say that elements in the same group have similar chemical properties. We already know that. So for example, group 1. Group 1, they all form +1 charge in their ions. Why? This is because all group 1, if they are in the same group, they have the same number of valence electrons. So this is because elements in the same group have the same number of valence electrons. Okay, but again, quite clearly, this one sentence won't get you 2 marks. So how then do you go on? So what if they have the same number of valence electrons? Elaborate. Hence, they meaning the elements in the same group, will lose or gain or share the same number of valence electrons when reacting. So let's say when they react with oxygen, all these elements in the same group will lose the same number of valence electrons when reacting with oxygen. So they will lose, gain, or share the same number of valence electrons when reacting. So their chemical properties are similar. This also means that you need to have the concept that chemical properties are determined by electrons. It's ultimately all about electrons, okay? So chemical properties is all linked to lose, gain, share valence electrons. All right. So if you want the chemical properties to be the same, then you have to lose or gain or share the same number of valence electrons. Finally, the last question. The last question is something we have taken for granted. We know the metals are on the left because we can see sodium, potassium. Sodium and potassium are metals quite clearly. So they are found on the left. Non-metals are found on the right. So why? Why is it that metallic character decreases from left to right? It goes from metal to non-metal, so the metallic character decreases. Why? The reason is because metal means lose valence electrons. So the Sec 3s you just learned ions. You have learned that metal, sodium, calcium, they lose electrons. So as we go from left to right, the number of valence electrons increases from left to right. We can clearly see this. Group 1, 1 valence electron. Group 3 or group 13, 3 valence electrons. Group 7 or group 17, 7 valence electrons. All right. So the number of valence electrons increases from left to right. So the tendency to lose electrons to form positive ions decreases. So let's go from the left to the right-hand side. Right-hand side got 7 valence electrons. It's so hard to lose 7 electrons. I'd rather gain 1. Okay? So at this juncture, if you are done copying and if you have thought through it and you understood, can you please give me a thumbs up so that I know I can move on? Okay, thank you. Now, the next few pages are just pages of information. Now, I would strongly recommend all of us to read the next few pages ourselves to get the information that you need. The information that you need is all about different groups. We go from the group 1. Group 1 is also known as alkali metals. And the reason is because alkali metals form alkaline solutions with water. So for example, under the chemical properties, sodium reacts with water, and this forms alkaline sodium hydroxide. So again, we recall sodium hydroxide is the hydroxide. Metal hydroxides are basic or alkaline. Okay, so sodium hydroxide, definitely alkaline. Now in your notes, I think the printing is more accurate because my printing, I think the formatting has run a little bit. There is the explanation to explain why reactivity increases down group 1. That means it gets more and more and more reactive down the group. It actually gets dangerous to react the group 1 metals at the bottom with water. So take for example cesium at the bottom. Cesium will explode when it hits water. Okay, so it's very, very important for us to know why reactivity increases down group 1. Now, then we move to group 7 or group 17. Group 7 or 17 are called halogens. Okay, we will explain what is meant by halogens later. But first, we need to know their melting and boiling points and their colors, which is on the left. For group 7 or group 17 elements, the melting point increases. So you go from gas, index number 1 is gas. In this case, fluorine, gas. The first member of fluorine is a gas. Then chlorine is a gas, bromine is a liquid. So you can see that the melting and boiling points increases. Now, besides melting and boiling points increasing, we also note that the color intensity increases. Now, another way to say color intensity increases is that the color becomes darker down group 7 or group 17. So you can clearly see fluorine is pale yellow. In fact, it's so pale, you wouldn't be able to see it easily. But once you go down the group to iodine, iodine is a black solid. Now for iodine, it's useful to know, iodine is a black solid. This is at room temperature, of course. When you heat up iodine, it sublimes. So iodine is one of those elements which sublimes. That means it converts from solid to gas. Now iodine, when it sublimes, it forms a purple gas. So iodine is a purple colored gas when it's heated up and sublimes. Okay, so I repeat, iodine can go from solid to gas. This is purple. Okay. Now, besides that, iodine can also be dissolved in water. Dissolving iodine in water forms a brown solution. Okay. So iodine does have various colors. As a solid, it's black. As a gas, it's purple. And as a solution in water, it's brown. Okay. So these are the physical properties, which are the melting and boiling points and the colors. Now, you will realize that for group 7 or group 17, they are very much the opposite of group 1. In the sense that for reactivity, group 7, as you go down the group, the reactivity decreases. It's less and less reactive down group 7. And the reason is because group 7 elements react in the opposite way. Group 7 elements, they don't lose, they gain electrons. Okay. Now I'll leave you to read the chemical properties, including displacement on your own. So for the Sec 3 students, I know we have not done displacement, but I would love for you to read this yourself. Now the idea is very simple. Displacement is basically kicking out. A more reactive element displaces a less reactive element from its compound. What does it mean? At first, bromine is together with potassium, KBr. They are coupled together. Then chlorine comes in. We know chlorine is above bromine, right? So we use the fact that reactivity decreases down the group. So chlorine is more reactive, so chlorine displaces, kicks out bromine from KBr. So chlorine is now together with K. Bromine is left all alone. So this is called a displacement reaction. A more reactive element displaces a less reactive element from its compound. Okay, you have displacement reactions for halogens. You also have displacement reactions later on for metals when you learn that chapter. But the principle is the same. A more reactive element displaces a less reactive element. Okay. Now, why call them halogens though? What does halo actually mean? Now, halo means salt. Gen means make. So we say that group 7 or group 17 elements make salts. And that makes sense. If you think about it, chlorine plus sodium forms sodium chloride. That's a salt. Iodine plus sodium, sodium iodide. That's another salt. So the idea is halogens react with metals to make salts. That's why they're called halogens. Okay. Now, noble gases, I will leave you to read on your own. I think it's quite straightforward. All you need to know is that noble gases, they have a fully filled outermost electron shell. Therefore, they do not lose, they do not gain, they do not share valence electrons. Hence, noble gases don't really form compounds with other elements. Transition metals, which are the metals in the center. Now, for the Sec 3s, you will realize that the transition metals are from group 3 to group 12. All right? That's because the new periodic table has given group numbers to the transition metals as well. For my Sec 4s, the old periodic table doesn't have group numbers for the transition metals. That's why the big difference between the old and the new periodic table is the transition metals. New periodic table has assigned group numbers. Okay? Now, but for my Sec 3s and Sec 4s, please take note, zinc. Many of you think that zinc is a transition metal. However, zinc is not a good example to say, because zinc is not a typical transition metal. Zinc doesn't display the properties of transition metals. For instance, zinc doesn't have variable oxidation states, meaning zinc doesn't have different charges. Zinc is always Zn2+. So for the Sec 3s, Miss Ng must have made you memorize zinc ion is Zn2+. 2+ means the oxidation state is +2. And indeed, the oxidation state of zinc is always +2. There is actually no other known oxidation state of zinc in its compound. Okay, so zinc doesn't have variable oxidation states. Next, zinc doesn't form colored compounds. The compounds of zinc are white solids. Okay, Ken? Now, I will leave you to read transition metals on your own as well. If you have any questions, please do approach me. Now, let's go straight on to page number 8, which is actually the new content typically taught at A level. Now, so far, we have been looking at groups, group 1, group 7, transition metals, noble gases. But how about across a period? So let's just choose period 3, sodium to argon. Now, if I just look at the element on its own, element, not the compound, element, you realize that the melting points show a trend, somewhat a trend, right? Sodium, magnesium, aluminium, wow, the melting point is pretty quite high. Silicon, super high melting point. Then phosphorus, sulfur, chlorine is very low. Now, melting points depend on the structure and bonding. Because to melt something, you are overcoming forces of attraction. The forces of attraction are ultimately dependent on the structures that you have. So sodium, magnesium, aluminium are easy. You have learned that these are metals, so this is a giant metallic lattice. So in a giant metallic lattice, you have strong electrostatic forces of attraction between the positive metal ions and the delocalized electrons. Okay. Now silicon, group 4 or group 14. Silicon has a very high melting point. That's because silicon has a giant molecular lattice. So in case you forgot, please highlight. Silicon's giant molecular lattice is similar to diamond. Similar to diamond. Diamond also has a very high melting point, okay? Why is the melting point so high? Because in a giant molecular lattice, you have strong covalent bonds, which require a lot of energy to overcome in order to melt the solid. Okay. Next, we move on to phosphorus, sulfur, and chlorine. Now, typically at O levels, we don't teach you P4, S8. But at A level, you will learn P4, S8Cl2. Cl2 you should know. Okay, but P4, phosphorus exists as a 4-atom molecule. Sulfur exists as a 8-atom molecule. Okay, so the structure of P4 looks like this. Okay, so this shape is called a tetrahedron. Okay, that's P4. Okay, then let me find space to draw S8. Now, S8 is pretty interesting, though I won't say that I'm an expert at drawing this. Yeah, this is S8. Now, S8 is called a crown-shaped molecule. The shape of this molecule looks like the crown that's put onto the king's head, okay? So S8P4. And that explains to you why you see for sulfur actually has a slightly higher melting point than phosphorus. The reason is because it's S8. The molecule of sulfur is just bigger. As a result of that, it's heavier. Heavier molecules have slightly stronger intermolecular forces of attraction. That's why it has a higher melting point. Okay. Next, if we look at electrical conductivity, it's quite obvious. Metals, good conductors of electricity. Non-metals, not conductor. The interesting one is silicon, of course. Silicon is a metalloid. Silicon is actually right on the dividing line between metals and non-metals. So we say that silicon is a metalloid. So silicon displays some properties of metals, some properties of non-metals. In particular, if I look at electrical conductivity, silicon does seem to conduct somewhat. It's not zero. So we say that silicon is a semiconductor. And that's why if one day some of you progress to poly or you progress to uni and study semiconductors, most of the time semiconductors are made from silicon because silicon is a metalloid. Okay, now today we will not have the time to talk about how semiconductors are different from conductors. We don't have the time for that today. But if you have the time one day, please do a quick search on semiconductors. Okay, I think a lot of it will come out. Okay, if you also have the time, you want to Google band theory of solids. Later on, you can Google that and see what comes out of it. Okay, if we have time one day, we should discuss this during the training as well. Okay, so that was the element on its own, Na, Mg, Al, not combined with anything else. Now let's look at two types of compounds, oxides and chlorides. First, we have the oxides. So oxides means combined with oxygen. So we have sodium oxide, magnesium oxide, aluminium oxide. All right. So these are giant ionic lattices. Silicon dioxide is giant molecular. Correction. Silicon dioxide is giant molecular. So again, this is something that you must try to remember. It's like diamond. Diamond is giant molecular. Silicon also giant molecular. Silicon dioxide is also giant molecular. Now, silicon dioxide is actually sand or quartz. Quartz is the rock, okay, where you find SiO2. Next, the oxides of phosphorus, P4O10. That's why you can see P4O10 has a higher melting point than SO3 because P4O10 is bigger. Bigger and heavier molecules tend to have a higher melting point. Okay, so you can see from the graph, P4O10 has a higher melting point, right? P4O10 is higher than SO3 because heavier and bigger molecule. Next, pH of solution. So this links very well to what we just spoke about today, the types of oxides. So sodium oxide, basic. Basic means the pH more than 7. Magnesium oxide, also basic. Now, aluminium oxide is amphoteric. We learned that. Amphoteric is zinc, aluminium, lead. Okay. However, it's insoluble. Because it's insoluble, the pH is 7. Next, silicon dioxide is acidic, but doesn't mean that the pH is less than 7. Oh, sorry, it's insoluble, that's why pH equals to 7. Correction, just now aluminum oxide is insoluble, so the pH equals to 7. So SiO2 is the same. If it's insoluble, obviously the pH is 7 because it's just the pH of water. Okay, it doesn't dissolve in water. So the pH you measure is the pH of water itself. Okay. Now, but you realize for phosphorus, sulfur, and chlorine, the oxides are all acidic and they form very strongly acidic solutions, pH 0 to 2. Okay. Finally, we have the chlorides. Now, the chlorides, okay, you can read yourself, but what's interesting that I always point out to students is aluminium chloride. Because this is always asked during prelims. You are always asked, why is this unusual? It's unusual because AlCl3 is actually simple molecular. All right, you might predict that AlCl3 should be ionic because aluminium is a metal. Metal plus non-metal should be ionic, but based on the data, you can tell that AlCl3 sublimes at quite a low temperature. It sublimes at 178 degrees Celsius. So this tells you it's a bit unique. It tells you it's simple molecular. All right. Ken? Now, so AlCl3 is worth noting. It's actually simple molecular. Now, AlCl3 is also quite interesting because in the solid state is AlCl3. But in the gaseous state, as you convert to a gas, as it sublimes, it will start to do this. Okay, so you can see, wow, from AlCl3, now you form Al2Cl6. AlCl3 looks like this. So Al2Cl6 actually looks like this. So what do you realize? What happened was two AlCl3 molecules came together to form Al2Cl6. Two molecules come together to form one molecule. Two identical molecules join together. So two identical molecules join together. This is called dimerization. Di means two. So two identical molecules join together. That's called dimerization. Then you see something very interesting. Oh, why did Mr. So write these arrows? Now, these arrows are there for a reason, okay? I didn't draw a normal covalent bond. I use an arrow to draw it because these arrows, they represent what we call a dative covalent bond. So you are used to covalent bonds. Covalent bonds involve sharing of valence electrons. A dative covalent bond is where both shared electrons came from the same atom. So if you think about it, a normal covalent bond is where you share one with me, I share one back with you. I share one, you share one, we each share one. That's a normal covalent bond. However, in a dative covalent bond, the two shared electrons came from the same atom. So in this case, both shared electrons are from Cl, not aluminium. So in this dative covalent bond, both shared electrons are from chlorine. Okay? So I'll give you some time to take this down. I know it's a bit late already. We'll just finish off with the behavior of the chloride in water and we'll end off at this page, all right? So once you're done copying with this, can you please give me a thumbs up so that I know that we are done on this page? Okay, are we done copying? Thumbs up already? Sorry, I didn't see that. For the participants in the Zoom meeting, can you hear me? Are we done copying? Okay. Yep. Okay, so the dative covalent bond also has a separate name. Okay, it's also called a coordinate bond. Same thing. All right. Same thing. Okay. So you will see this appearing in some of the database questions that you will do later on as you practice the papers. And that's why I thought it's a good idea to introduce you all to some of these terms using aluminum chloride as an example. Okay, so for my pure chem students, you also realize that this process is reversible. What this means is that for this reversible process in equilibrium, we can do some changes to the system to make the position of equilibrium shift to the left or shift to the right. Okay, so this will be the topic of Le Chatelier's principle. Okay, but let's not go into that now. All right, the behavior of the chloride in water. Now, these are the behaviors of the chlorides in water. So you can read yourself. However, there's a difference between hydrolyze and dissolve. Dissolving is not a chemical reaction. Now, what does it mean? When I dissolve sodium chloride in water, it's not a chemical reaction. It means that no new products are formed. If I dissolve NaCl in water, it's still NaCl. It's just NaCl aqueous. However, hydrolysis is a chemical reaction. Okay, so AlCl3 hydrolyzes. This means that AlCl3 reacts with water, and this produces new products. As you can see, AlCl3 produces HCl. That's a new product that is formed when AlCl3 reacts with water. Okay, so similarly for SiCl4, PCl5, S2Cl2, and so on, this is all a chemical reaction. They react with H2O and form something new. Whereas sodium chloride and magnesium chloride just merely dissolved. They didn't form a new product. Okay, now, in case you're wondering, do you need to memorize these things? Now, the answer is not really. You don't have to memorize these reactions and what it forms. However, it is a good idea to start accumulating experience in doing chemistry, experience with different chemical knowledge through reading. And that's why you are joining Olympiad, is to build this sense of awareness for different facts in chemistry. So I would say for Olympiad, do make it a point to learn these. All right. So let's stop here for today. I know it has been a long day. So thank you for your attention. Okay, I shall stop the recording here. Thank you.